Hello, AP Calculus students. It's Mr. Ford here with another summer packet tutorial, and we are on into, I think, the top third of the alphabet, topic P. We're almost done with the packet, honestly. I would say, actually, let me start this video by saying that from this point forward, this would be kind of where I draw the line between maybe what I might consider to be an Algebra 2 topic and what I would consider probably to be a pre-calculus topic. So we have logarithms and some geometry review, but then after that we enter into the trigonometry realm. But I don't mean to get too off track. Let's just talk about topic P today. So topic P is exponential functions and logarithms, two things that go hand in hand. You cannot have one without the other. So if you're ever confused by logarithms, just remember that a logarithm is nothing more than the opposite of an exponential function. Actually, a good way to think about logarithms is to think about them as exponential functions, and I'll tell you exactly what's going on there. So an exponential function is something that we usually define to be in the form of a times b to the x power. Some sort of a as a constant, sort of a starting value, and b is kind of the multiplier. So a logarithm is pretty much the same thing, but backwards. So in this case, I would say that the logarithm of base b of y equals x. Now, what I think is going on here, the way I try to explain logarithms, so let me just think about this for a minute. Let me draw you a picture. When we talk about logarithms, let's think about the example would be 2 to the x power. Let's think about that on a number line, maybe, and we'll maybe help us give a little bit of thought to this. So the starting point, 2 to the first power, well, that's just going to be 2 every time. And then if you multiply 2 by itself twice, you're going to get 4. If you multiply 2 times 2 times 2, you're going to get 8. 2 times 2 times 2 times 2 will give you 16, and so on. And so what we're building is building this number line, this idea, pretty straightforward way of thinking about exponential functions, where to go to the right on this number line, it looks like we're doubling. We're multiplying by 2. Times 2, times 2, times 2, times 2. Seems to be the pattern here. Well, if multiplying by 2 is how we go to the right, then how do we go to the left? That's the next part of the conversation. So, for example, what's 2 to the 0 power? Well, if you do the math or do any sort of algebra tricks, you guys already know anything to the 0 power is 1. And, of course, to go back in time on this number line, we would divide by 2, and 2 divided by 2 is 1. And that's why, as you go into negative territory, 2 to the negative second power, 2 to the negative third power, negative fourth power, you're going to get the same numbers, but this time they're going to be on the bottoms of fractions, because 1 divided by 2 is 1/2, and 1/2 cut in half is 1/4, and that is 1/8, and then 1/16, and so on. So you end up with the same numbers, but they are 1 over each other. Now, you already knew this. This would be an exponential thing, an exponential system. What a logarithm comes by and says, if I say this is a logarithm base 2, and if I say, what's the log base 2 of 8? What I mean is, in a system that counts by multiplying by 2 every time, how many steps to get to 8? How many steps to get to number 8? And the answer there is 3. It takes 3 steps. And in this case, what I mean by saying that logarithms and exponential functions are the same thing, I'm saying that 2 to the third power equals 8 is the same as saying that log base 2 of 8 equals 3. These are the same statement. They are saying the same information, just backwards. So with this in mind, let's go and take a look at some of these examples. I think you'll be surprised how easy these are. Now, most of you do have a calculator handy, and if you don't have one now, I'm sure you could Google one right now that you could just tell, hey, log base 2 of 1/4, what is it? Well, it would be better to understand why the answer to this question, for example, is -2 in this problem. In fact, let's go back to that number line, because this first one is exactly that logarithm, log base 2. It's saying, okay, in this system, log base 2, how many steps is it to get to 1/4? Well, you're starting off at 2, but 1/4 is right here at -2. In other words, in a system that counts by multiplying by 2 every time, to get to 1/4, you have to go back in time 2 steps, -2. And that's why the answer is -2 in this case. But let's say we don't have that whole number line set up. Well, let's think about number 2, for example. Now, this is an interesting one. Log base 8 of 4. Well, we got to think about a number line where we're multiplying by 8 every time, and 0 is always 1, and the first step, 8 just by itself would be 8. So really we're asking, where is 4 in here? It's somewhere in between 0 and 1. Our answer is going to be some number between 0 and 1. But the problem what makes this a challenging question to answer is how many steps does it take? Well, let me think about that question again, just off the cuff here. What makes this question tricky is this is a times system. To get from 0 to 1, you are multiplying by 8. And so the question is, how do you break up multiplication of 8 into 2 equal steps or more, or any sort of steps that land on 4, for example? Well, in this case, what we want to do is split up that multiplying of 8 actually into 3 steps. And I'll show you what I mean, 1/3 and 2/3. Because, to get multiplied by 8 is the same as multiplying by 2 3 times. Times 2, times 2, times 2. And this is my explanation as to why the answer to this question is 2/3. Because to get in a system that counts by multiplying by 8s, you have to go 2/3 of the way to 1 to land at 4. Because we're multiplying the same thing each time. That's why the answer to this question is 2/3. Now, if you wanted to think about this in a more traditional sense, you might rewrite it as an exponential equation, and that equation would be 8 to what power equals 4. Now, typically in a problem like this is the way Algebra 2 textbooks will say to solve this problem, is they'll say, okay, we can rewrite 8 and 4 as powers of 2. So you can rewrite this problem as 2 to the 3rd power to the x power equals 2 to the 2nd power. And that's fine. I have no problem with this method at all. Another way of saying the same thing is 2 to the 3x power equals 2 to the 2nd power. And now you can say that 3x has to equal 2. And that's why x is 2/3. So there's just 2 different ways to think about it. The top, this would be the more like Bob Ross artistic version of why the answer is 2/3. This would be the more like Algebra 2, like, hey, here's a set of steps. Let's try number 3, and we see for the first time of many in this class, we're going to see the natural logarithm pop up. A ln is known as a natural log, and it's really just a log base e. What's e? E is well, again, you have to learn calculus to explain what e is in the first place. It's a really important number, but it's hard to explain why it's important in high school math. So you learn about it in high school math so that later on in a college math class, you can have more fun with it. But the first thing to do here, I think, is to rewrite this as a power of e. This is equal to the natural log of e raised to the negative 2/3 power. Again, I'm taking the negative 2 from the fact that it's the 2nd power on the bottom, and the 1/3 from the fact that there is a root there. Now, what you might want to know, an important case, natural log of e is equal to 1. So what's going to happen here is that negative 2/3 is actually going to kick down into the main line with everything else. Natural log of e cancels out, and so our answer is negative 2/3. If I'm showing all of the work here, there's 2 properties of logarithms that are happening here. The first one is that when you have a log base anything of b to some x power, you can take that x power and multiply it in front. These are the same statement right there. So the first rule I'm doing is taking that 2/3 out of the exponent and multiplying in front. And then I'm using this fact that the natural log of e equals 1, which is actually an extension of another logarithm rule that log base b of itself equals 1. Then I'm saying the answer is negative 2/3. Looking back on it, I'm not proud of the way I explained the answer to that question. Probably should have done some more work on log rules, but it looks like if I'm looking ahead at 4, 5, and 6, we're going to get a good chance to talk about that right now. So let's talk about some logarithmic properties. So 5 to the log base 5 of 40. The short answer to this question is the answer is 40, because all that other stuff cancels out. Let's talk about why. There is a rule out there. You probably learned about it at some point in your pre-calc class. I am not assuming, by the way, that anybody knows this rule is true. But b raised to the log base b of x power equals x. In other words, the b and the log base b kind of just cancel out, is what's happening here. The way this works, if you would want to write this as a logarithmic expression, what you'd be writing here is that the log base b of x equals the log base b of x. They're the same thing, the same exact idea. So anyway, it's 40. The 5 and the log base 5 cancel out. The same way that e to the natural log of 40 would also be 40. That's a property we use a lot later on in the class too. And here we have that same property right there in number 5. This is using the exact same property. In this case, this is e to the log base e of 12, and those things all cancel out, so the answer here is 12, like that. Things to look out for. Don't beat yourself up if you don't memorize it in the first pass. Nobody does. Just be wary of it. We'll have a lot of time to deal with logarithmic rules in the class also. Here's another classic logarithmic rule. If you have a log base b of a and you're adding to that a log base b of some other capital B, for example, you can take those a's and b's, the capital A and B, and you can multiply them together. This is the log base b of a times b. So essentially what we're going to do here is combine all three of these together. This will be the log base 12 of whatever 2 times 9 times 8 is, which is some number. Man, I'm not so good at math in my head. 9 times 8, 72. 2 times 72 is 144. So this is the log base 12 of 144. You might be tempted to stop this right now, but actually we can answer this question, because in a system that counts by multiplying 12 every time, how many times do you need to multiply 12 by itself to get to 144? And the answer here is 2. The reason being there is that if you go to the number line for a minute, here's 0 and 1, here's 1 and 12, here's 2 and 144. Because if you're counting by multiplying 12 each time, it takes 2 steps to get to 144. Pretty slick. Let's go on to some other ones here. We got a lot of time to practice a lot of these examples. This one's going to be very much the same as the previous one. Let's start by using that logarithmic property to multiply 2/3 and 3/32 together. So we'll start with log base 2 of 6 over 96, which I suspect reduces. Hang on, stand by. Let me confer with the old phone calculator here for a minute. I guess you should suppose I am cheating a little bit. This is the log base 2 of 1/16. 6 goes into 96 16 times. And this is, again, a question we can talk about by conferring our little chart that we made at the beginning of this video. Because in a system that counts by multiplying by 2's, how many steps does it take to get to 1/16? Well, that's 4 steps back in time, -4. So log base 2 of 1/16 is -4. One thing you might notice is that whenever you take the logarithm of a fraction or a decimal, you get a negative number because of the way exponential equations work. It's a thing to keep in mind. Also keep in mind your logarithms will never give you 0 because of the way exponential functions work. They never actually get to 0. They just divide over and over again. So you'll never see it happen. Let's talk about number 8 here. Okay, now we got subtraction. Well, if the rule with plus signs means we're going to multiply together, then subtraction signs should mean division, and that's true. The log base b of, again, capital A minus the log base, I got to really use different variables here, b of, let's say capital C, just to make it a little more varied. This would be equal to the log base b of A over C, like that. So we're going to use this rule right now. We're actually going to divide 4/3 and 12. So we'll combine these together. We have the log base 1/3 of 4 over 36. And all I'm doing there is 4/3 times 1/12. Instead of dividing by 12, multiplying by 1/12. A really helpful trick to get around a lot of division situations. Now, 436, of course, can reduce. This is the log base 1/3 of 1 over 9, like that. And so here we have another common logarithmic question. In a system that counts by multiplying by 1/3 each time, how many steps to get to 1/9? Well, let's talk about, I'll give you the answer right now is 2, but then we'll talk about why. This is kind of flipped a little bit. This time you're starting at 1. You always start at 1. After 1 multiplication of 1/3, you're at 1/3. And at 2, this is a times 1/3 number line, by the way. After 2 multiplications, you're at 1/9. So, again, in a system that is multiplying by 1/3 each time, it takes 2 steps to get to 1/9. Now, I know this seems like a contradiction of what I just said about the fractions giving you negative numbers, but keep in mind that this time the base of the logarithm is actually a fraction itself. So as we go to the right, we're going to get smaller numbers. If we go to the left, we get bigger numbers. That's the opposite when it comes to something with a whole number like this one. Okay, to handle this question, we're going to use another property of logarithms. We already mentioned it earlier ago, but probably the most commonly used and most algebraically powerful. If you have a log base b of, say, some number to the x power, like this, then you can kick that x down to the front and multiply it, x times log base b of a. That's what we're looking for there. This is the most commonly used, I don't know what it's called, but Now that fifth power is just begging to be kicked down in front, but 3, the square root of 3 rather, is also an exponent. So let's keep that in mind. This is equal to the log base 3 of 3 to the 5 halves power. Keep that in mind. That is the 3 to the 1/2. Well, let me not skip steps in this instructional video here. This is 3 to the 1/2 power to the 5th power. So this is log base 3 of 3 to the 5 halves power. Now, what we're going to do now is we're going to take advantage of the property that's right there. We're going to kick that 5 halves off in front. 5 halves times the log base 3 of 3. And then we're going to think about a really easy logarithmic property that we have mentioned already, but let's explain a little more. In a system that counts by multiplying by 3, well, how many steps does it take to get to 3? Well, it takes 1 step. This is a common, we already talked about it in this video, in fact, but the log base b of itself is always equal to 1. Because this is the equivalent of saying that b to the first power equals b, which is true. So this is just 5 halves times 1, or 5 halves for number 9. Let's talk about some logarithmic equations now. We're going to get a little bit fancy with these. Number 10, we have log base 5 of 3x minus 8 equals 2. What we're going to do here is we're just going to rewrite this as an exponential equation instead and then just solve it. Because, well, so we call this the number shuffle when it comes to logarithms, but the log base b of y equals x is the same as saying b to the x equals y. These are the exact same statement. They're just rewritten. A logarithm is not a function so much as it is a way to rewrite an equation to think about exponential equations in a different way. So we're just going to rewrite this. If we're following that number shuffle, the base of the log is now the base of the exponent. The exponent is what was originally on one side, so that's 5 to the 2nd power, equals whatever the argument is, 3x minus 8. And now this is an easy problem to solve because this is just 25. So from here you can solve it as you would normally. 32 is equal to 3x, and would it kill you to make a whole number answer here? Jeez, 32 over 3, which is something. 10.6 repeating. There you go. Is there a, unless I made a math mistake. Oh, I made a math mistake. When you add 8, it's 33. I'm a ding dong. Don't at me. If you're watching this in the middle of the summertime and you see my math mistakes and you're like, I don't even know who this guy is, that would be a fair thing to be concerned about. Ugh. Okay, number 11. Same exact game here. We're just going to take the base of 9, raise it to the 1/2 power from the right side, and set it equal to x squared minus x plus 3. 9 to the 1/2, of course, is the square root of 9, and that's 3. And since 3 is on both sides of this equation, we can ignore it. We can just do that. And that's going to leave us with a nice 0 on this side. And let's go ahead and factor in x out of those guys also. So there actually are 2 answers here. Looks like x could be 0 or x could be 1. Those are the 2 numbers that will make both of the multiplication parts equal to 0. Right there. So we have 2 answers, 0 or 1. Number 12. Okay, so this one we're going to do pretty much the same thing we did in the last problem, but we got a couple things to talk about. First thing we're going to do is use that plus rule that we mentioned earlier to combine these together. This is going to be 1 log of 5 times x minus 3, which equals 2. Now before we distribute that, you might be noticing that there is no number underneath the word log, and that's because this is what's referred to as a, quote, common log. And it's the other log that you are just expected to know next to the natural log. If you ever see log by itself, this is the way of saying log base 10. That's it. So it's a base 10 logarithm. Your calculator has 2 buttons pre-programmed on it. There's common log, where it just says log, which is base 10, and then natural log, which is log base e. These 2 get nicknames. You are expected to just know this, which, as much as that sucks, as a math teacher, I'm always frustrated by things that we just expect students to know, but that's one of them. Anyway, so we're going to rewrite this. This is 10 to the 2nd power, which equals 5x minus 15. And then from here we can solve the problem as we would normally, because 10 squared is just 100. We get 115 equals 5x. I have no idea what this is. I need a calculator. No, I can do this. I can do this. I can do this. Because 5 goes into 125, 20 times. And then I would need 3 more to get to 15. So 23. Calculator, schmalculator. No problem at all. Okay. We got a handful more of these. Let's just crank through them. Here we go. We're going to use the exact same properties. I'm going to pick up the pace a little bit because this one is really repetitive, this particular worksheet. So here we go. First thing we're going to do is combine these together. This is log base 2 of x minus 1 times x plus 3. We'll have to factor that, which equals 5. So let's rewrite over here. We're going to have 2 to the 5th power, which is 32, equals x squared minus x plus 3x minus 3. This is 32 equals x squared plus 2x minus 3. 0 will equal x squared plus 2x minus 35. And let's see if we can factor this. What multiplies to negative 35 and adds to 2? 7 and 5. Haha. Plus 7 minus 5 to get that good positive 2. So our two answers here would be x equals negative 7, which is the one that makes that 0, and x equals 5, which is the one that makes this 0. There we go. Number 14, let's start by combining these. This time we got to divide because we have a subtraction sign. So this is log base 5 of x plus 3 over x, which equals 2. Let's go ahead and rewrite it as an exponential. That's 5 to the 2nd power is equal to x plus 3 over x. That's 25, which equals x plus 3 over x. Let's get that x out of the bottom of the fraction. Let's multiply everything in the problem by x. This will leave us with 25x equals x plus 3. I'm going to move up here because I ran out of room. That's 24x, which equals 3. And that means that x is 3 over 24, or 1/8. I like that for an answer. Pretty good. Number 15, we have natural logs here. Just remember, those are regular logarithms, just base e. So this is a natural log of x to the 3rd over x squared, which equals 1/2. Might be a good idea to combine those two. X to the 3rd, well, that's just x. This is just natural log of x equals 1/2. Now if we rewrite it as an exponential, we'll be done. This is e, which is the base, raised to the 1/2 power, which equals x. And this is one of those ones that's tough because students are like, well, what's that? What's e to the 1/2? You circle it, man. You're done. Hey, have we talked about b real before? Oh, it's time again. Look at this. Hey. Sorry, this video get interrupted by b real, the social media of the future. Okay, cool. You get 2 minutes to take a photo of what you're doing at that exact moment in time. I'm doing this. Hopefully you had fun watching it and didn't just skip ahead. Okay, number 16, here we go. Now these last set of problems here, we're going to take advantage of a few different ways of solving them. 3 to the x minus 2 power. So the challenge here is how do you get that x out of the exponent? And I'm assuming, actually, I got to be honest with you. From this point forward, we've entered into the calculator zone. We will not use a calculator to get the decimal answers for this, but you would need one. And I'll show you how to get around this without a calculator. But this point forward is the calculator zone. You would need a calculator to get the exact answer for this. So the thinking here is that 3 to some power is 18. I don't know what it is. I know that 3 squared is 9, and I know 3 to the 3rd power is 27. So I know somewhere. Again, think about that number line. It's like, here's 0, there's 1. 1 is 3, 2 is 9, 3 is 27. Somewhere, 18. 18 is somewhere in here. I don't know where it is, and it's going to be a weird decimal at the end of the problem, but that's kind of the thinking. How do you solve a problem like this? What we're going to do, we're going to use a really common algebra trick that you do when you're solving this. This is why you learn about logarithms, especially because of that power rule. What we're going to do is we're going to take the logarithm of both sides of the problem. And what that will do is it'll cause the x minus 2, where the variable is, it'll cause that to kick out of the fraction where we can now work with it where we want it. We can solve it for x. We can isolate x, which is what we always want to do. It does not matter what logarithm you choose to use. The standard choice would be a natural log because that's the one that gets used the most in high school math. So let's do that. I'm going to write it out the long way just this once. We're going to take the natural log of 3 to the x minus 2 power and that's going to equal the natural log of 18. Again, the principal idea of solving a problem like this is that you can do whatever you want on both sides as long as you do it to both sides. Now, natural log of 18, we should point out, that's just a number. It's whatever power you have to raise e to get to 18. It's a decimal. Your calculator can tell you what it is. I don't know what it is, but your calculator can tell you. But most importantly, we're going to take that x minus 2 and kick it out in front. X minus 2 times the natural log of 3 is equal to natural log of 18. And the cool thing here is now we can actually just solve this for x the way we want to. Because natural log of 3 and natural log of 18 are just numbers. I don't know what they are. They're going to be weird numbers, but you could divide both sides by natural log of 3 if you wanted to. You could. And that means that x minus 2 is whatever that ratio is. Natural log of 18 over natural log of 3. And then all you got to do is add 2 to it, and you got your answer. So x is equal to whatever the natural log of 18 over the natural log of 3 plus 2 is. This is the exact answer, like this. To get the approximate answer, you would need a calculator for this. I can tell you because I'm looking at it on another monitor, it is about 4.6309. Which tracks, because if you subtract 2 from it up here, you'll get 2.6309, and 3 to that power is 18, which fits what we kind of thought about at the beginning of the problem. That's how all these problems are done. This next one actually will kind of have a, well, it won't. I thought it might for a little bit, but number 17, 17 and 18, we're going to solve the exact same way. They're going to get a little algebraically hairy, but they're both solved the same, use the same method. For number 17, we're going to take the natural log of both sides. Now, I'm going to go ahead and do that 3x plus 1 kick down right now because I want to save some time. 3x plus 1 times the natural log of e is equal to the natural log of 10. Again, taking the natural log of both sides and kicking that thing down. Natural log of e, you might know, is just 1. So we can just kind of ignore it because it doesn't do anything. So the rest of this problem is just getting all the non-x stuff on the right side of the equation. So 3x is equal to natural log of 10 minus 1. Then if you divide the 3 over, you're done. X is the natural log of 10 minus 1 over 3. Ta-da! Does that answer mean anything to anybody? No, but that's exactly the correct answer. Again, your calculator can tell you about what it is. It's about 0.4341. Pretty cool. Number 18, again, this video is creeping up on 30 minutes, which is longer than I wanted it to be, but this is a heavy topic for this class. So again, we're going to take the natural log of both sides and kick the exponents down. So we'll have x times the natural log of 8 is 2x minus 1 times the natural log of 5. And again, the game here is just to isolate the x, get the x by itself. So I think to do that, we're going to have to distribute that natural log of 5. So we'll have x natural log of 8 equals 2x natural log of 5 minus the natural log of 5. This would be, by the way, the standard way to write a logarithmic expression involving a variable. It goes after the variable. What we're going to do now is subtract the 2x natural log of 5 over to the other side. Again, all we're doing here is subtracting this entire quantity from both sides. And it cannot combine. It looks like it might be able to, but it doesn't. Now, we're going to go ahead and use a common algebra trick. We're going to factor out the x from what we're doing here. We're going to get rid of that x. Pull it out because we want to keep it by itself. This is natural log of 8 minus 2 natural log of 5. And we are pretty much home free because the last thing we got to do is divide that entire chunk over. And again, will it be pretty? Nope. But will it be right? Absolutely. X is equal to the negative natural log of 5 divided by the natural log of 8 minus 2 natural log of 5. That is what it's supposed to be. If you want to try it on your calculator, that should be about 1.4124, which is suspiciously close to the square root of 2, but I don't think that's what it is. Anyway, there you go. This one, I got to be honest, is a little more instructional than the other ones. Spent a lot of time at the front talking about logarithms and how they work. Looking back on it, it looks like a lot of stuff, but just take your time with it. Go nice and slow. Again, this is one that, you know, if you didn't do this one in one sitting, I wouldn't blame you. That's a lot of stuff to do for this one session. So hopefully this video was of help to you. It's important. You know, I make a lot of these videos throughout the school year. It's important. I say a lot. You should watch them. You follow along, write the answers down as you go, sure. But just keep your brain on while you do that because I'm usually explaining everything as we go too. Different ways of looking at problems. All sorts of things. Don't forget also, you are awesome and smart, and you can do this. You are smarter than me, probably. And you can do this. You absolutely can. I believe in you. I'm really proud of you for choosing to take the class. I can't wait to work with you guys in the fall. And have a great summer. I hope you're doing something fun today. I'll see you in the next video.